That's right. We have one example left to go. It's example 9. We are going to roll right into the next section. So if you would like to begin downloading 2.6 while you're tuning me out so that not everyone's downloading it at once. I don't know, can you download it in the background while you're working? No. But feel free to be downloading it if you want, if you're comfortable with it while we go through this. So on example 9, we are given some information again, but we're not given a graph of velocity or position, and we're not given an equation. We can represent a function that represents speed, it could represent speed, velocity, acceleration, or position by a table of values. So that's what we have here in example 9. It says the values of the coordinate S of a bug moving smoothly and continuously. Along a line for various values of t equals 0 to 4 closed interval are given below. So if it's moving smoothly and continuously, that means that its path is smoothly connected, which we can infer then is what? Differentiable, yeah. And of course continuous. It says that explicitly. So the first thing you want to do when you're given a table of values is to say, okay, what is it the table of values of? We have the position function. It tells us where it's at. The next thing is, what are the values given? Well, we're given values all the way from 0 all the way to 4, which happens to be the interval that they're telling us. Sometimes you might have extra values in the table, like I could give you values at 4.2 and 5, and those would be irrelevant then when you're looking at the interval from 0 to 4. So be mindful of that. The next thing I would say is look for units. Just be mindful of units from the beginning. Do we have any units in this problem? I don't see units anywhere. So that kind of liberates you from the responsibility of putting any kind of units on your numeric answers or on your verbal descriptions, which is, it's kind of nice, okay? So let's go ahead and answer the questions then. What is the displacement of the bug on the closed interval from 0 to 4? Show the work that leads to your answer. Displacement, remember, is your net change in position, which should be your final position minus your initial, right? And if we're looking from 0 to 4, and our function's name is s now, not x, it's just s of 4 minus s of 0. Is this bug moving on a horizontal line or a vertical line, or does it say? No, so we got linear motion in general. We know it's moving along a line. That's really all that matters. Okay, so now I'll pull those values from the table, and hopefully they're there. 0.2 minus s of 0 is 40. 0.0, I guess that's pretty accurate right there. And on a free response, would you stop here, or could you stop there? Yeah. Do we have any units to put there? No. Is that going to be a multiple choice answer? No. If you stop there on a free response, would you be able to sleep at night? That's up to you. I don't know. I probably couldn't. So I would probably simplify and call it negative 39.8, right? Yeah. Right. If you owe somebody $40 and you pay them back 20 cents, you still owe them $39.80. Wow. Right. Probably so, yeah. So what, again, this means is over that 4, we can call it seconds or days or whatever, the bug is 39.8 units to the left or below in the negative direction from where it started. That's what we know. All right, what is the minimum number of times the bug changes direction? Explain your reasoning. What is the fewest number of times the bug changes direction? How are we going to do that? It moves smoothly and continuously, right? So this is kind of an IVT thing, right? There's no way that it can go from one to another without passing through everything in between. Let's see what it does. We know as we go from left to right, it goes from 40 to 35, right? So I know it's going, let's just say down for the sake of movement, up and down. Is that okay with that? Let's say since the y values are decreasing, it's just convenient to say, let's say it's moving down on a vertical line. It moved down 5 units. Could it have gone up first to 43 and then come down to 35? Yeah, and it would have changed directions there, but is there a guarantee? No, so we can't assume that. And then from 35 to 30.2, that's going down again. It's decreasing. Now from 30 to 36, That's now coming back up. So there's the first time where it had to have changed directions, at least once. Now from 36 to 48, it's going up again, so it doesn't necessarily change directions there. 48 to 45, that got smaller, so now it's going down, so it has to change directions one more time at least. And then 45 to 48, that's down. And then 38 to 16, that's down. And then 16 to 0.2, that's down. Now, in between any of those intervals, it could have done whatever. You know what bugs do, right? They're totally unpredictable. But we know for sure at least it had to change directions at least what? At least twice. So what is the minimum number of times? 2. That could be your answer. Or if you want to spell it out, 2. But don't spell it like this. Okay? Or the other way. Should be this, right, if you're in Louisiana? Or is that toe? I don't know. That's toe. Okay. It would be, I guess it would have to be 2? 2? I don't know. Let's just say twice. How about twice? Twice would work. Or 2 times, or whatever. Okay, so 2. Now, the next part is, that's a sentence. Put a period after it. What's the minimum time the bug changes directions? We just answered the question. But now the reasoning. So maybe common sense. Who wants to take it?
Yeah, how would you word that?
That's what I'm asking you. How do you word it? Just left to your own devices. Since the position goes from decreasing to increasing? Yeah? And then the position goes from increasing to decreasing? Something like that? There's going to be a way to talk about that later on using what's called the MVT, the mean value theorem, which talks about it's like the IVT for slopes, okay? So without the MVT, which would be a better argument later on once we learn it, right now we could just say since the position goes from decreasing to increasing, where does that happen? Yeah, on the interval from 1 to 1.5 and increasing to decreasing somewhere on the interval from 2 to 2.7. Do we need to say something about the fact that the bug is doing this smoothly and continuously as well? We kind of do. That's part of the reasoning, right? Because even though they told us, it is an important part of why we know it has to change direction, because it can't just be in one place and the other without changing directions. Since the position goes from that to that in increasing, and since the bug is moving smoothly, because that addresses the derivatives, which are the slopes, which what we're talking about when we say increasing, decreasing, and continuously. So it can't teleport from one to the other without changing directions. So later on, we're going to be using the mean value theorem, which will make this a little bit stronger argument. Okay. Okay. What is the bug's average velocity on the closed interval from 0 to 0.5? Show the work that leads to your answer. Does average velocity require any any calculus? No. Does it require any algebra? Yes, yes. The average velocity, remember, is your displacement over time. It's your change in position. So that would be s of 0.5 minus s of 0, all over 0.5 minus 0. Now, again, when it says to show the work that leads to your answer, it's super important to show that. That's called the what? That's called the difference quotient. And even though we all know that 0.5 minus 0 is not 0.7, but rather 0.5, we still have to show it because it's a quotient of two things being subtracted. Now we can go ahead and plug in values from the table, which, oh, by the way, if you didn't want to put s of 0.5 minus s of 0, what is s of 0.5? 35, right? You don't have to even put 0.0 because it looks like it terminates. S of 0 is 40, all over 0.5 minus 0. Does that also show a difference quotient right there? Does that show a quotient of two things being subtracted? Yes. So this could also work for getting credit for indicating your method, but it's also a numeric answer, right? So this is what I will refer to throughout the year as a twofer. It's a 2-for-1. Okay, it's a 2-for-1 because it indicates your method. It shows the difference quotient, but it's also a number. And because there's no units to add on the end, you could stop right there and you're going to get full credit. You don't even have to simplify. It's a difference quotient and it's a number. Now let's proceed in case this happens to show up on a multiple choice question. Without a calculator, 35 minus 40 is negative 5. 0.5 minus 0 is 0.5, also known as 1/2, which dividing by a half is the same as multiplying by 2, and we get negative 10. Yeah. And again, there's no units there, so you don't even have to add units of distance over units of time. Just leave it. No units. But that means that the bug's position was on average what? Increasing or decreasing? Decreasing on average on the interval from 0 to 0.5. And I just broke the tip of my stylus. Yay, me. All right, I want you to do part D then on your own while I repair. Estimate the bug's velocity at each of the following. Use proper notation always, that goes without saying, and show the work that leads to your answer. Now, let me get you set up while I retrieve another tip for the stylus here. I'm trying to approximate the velocity at a single moment in time. That means I'm trying to find the, not average rate of change, but the what? Instantaneous. I'm trying to find the derivative value. Now, from a graph, you can find derivatives without an equation if you can find the slope, like of a line. Of course, from an equation, you can find the derivatives by finding the derivative function and plugging in. There is no way, though, from a table of values to find the actual value of the derivative. So that's why the bug's velocity is not expected to be calculated exactly, but rather calculated as simply an estimate. Now, whenever the College Board uses the word estimate or approximate in the instructions, you must be on high alert, and the alert is squiggle alert. You got to be on squiggle alert, which means in your calculations, you need to put squiggles. Whenever you round or truncate the 3 decimals, you don't have to put squiggles. But when it says estimate or approximate, you do. Now, how are you going to approximate the slope if you can't use calculus? You have to fall back on what? Algebra, which means you're going to need how many points? 2. So if you're trying to approximate the slope at 0.5, how could you approximate the slope at 0.5? You need another point. Which points can you use? You could use the point to the left because it's only a half unit away, so you can find the slope of the secant line there. You can use the point that we're interested in and the point to the right because it's also only a half unit away. You could also legitimately use the point on the 2 points on either side. That'd be kind of how your calculator would do it. So there's 3 different ways you could do that. Go ahead and find all 3 ways if you want and show the difference quotient, and I'll catch up with you here. This is where it's not real fun on the iPad. You have to kind of scroll back and forth and zoom in and zoom out. three different ways to calculate it. Here's where the squiggles comes in. If you're trying to approximate the slope at 0.5, that's the derivative of s. So you need to put s prime of 0.5, and then that's where the squiggles would come, the approximation symbol. Because now it's only approximated by the slope of the secant line. Now, I didn't put like s of whatever. If you use the values from the table in your difference quotient, and we can see that these values are coming from particular places. So this would be using 0.5, the point of interest, and 0, the point to the left. So what's important when you're doing the difference quotient is, remember, the table above, the first row at the top are the independent variables, and the second row are your dependent variables. But when you set up your difference quotient, they have to be what? Flipped. So it's very easy, if you're not thinking, to put change in x over change in y instead of change in y over change in x. That can earn 1 out of 2 if you do that. But you want both points, don't you? Difference quotient and then the number. So this one gives you negative 10. If you use the point of interest and the point to the right of it, which would be the point 1, comma 30.2, then get in the habit of doing final minus initial. Even though, remember, the ratios don't matter as long as it corresponds, because this can give you the average velocity, or the top gives you the displacement. That one gives you negative 9.6. And the top one, if you use the 2 points on either side at 0 and 1, you get negative 9.8. So they're all pretty close. Now, sometimes they won't even really be close, but in this case, they kind of are. Now, you wouldn't even have to simplify on a free response, right? You could just stop with that numeric difference quotient, that numeric difference quotient, that numeric difference quotient, and any one of the three would be viable because the 2 points on either side are equidistant. Now, let's do the same thing at 2.7. So I'm going to go ahead and start by saying s prime of 2.7. What comes next? Squiggles. And now I'm going to come up here to the chart. The chart. I'm going to come up to the chart. Yeah, which is also called a table of values. And I'm going to look for 2.7, and I see it. And I see it in the table of values. So, if I look to the left, I have another point that is 0.7 units away, right? If I look to the right in the table, I see another point that's only 0.3 of a unit away. In this case, I guess you could, by the same argument, use any one of those three methods for before, but because 0.3 is closer than the one that's 0.7 units away, we're going to use those two right there. So if they're not equidistant, use the point of interest and the one that's closer to it. Now I can just use the difference quotient, so 38.2 minus 45. All over, and then the change in the corresponding y values are 3 minus 2.7. 3 minus 2.7. Yeah. Okay, so there's that one. One way to do that one. The points are not equidistant, but the point that we're interested in, 2.7, is still in the chart, which Al Roker and I now both use that word very carefully. Yeah, Al Roker knew what he was saying. At 3.5, the first thing I'm doing is s prime of 3.5, squiggles. Squiggles. S prime of 3.5, squiggles. All right, if you're at home and you're listening or you're in class listening, you can just Google Al Roker chart and see if Google recommends a different spelling. Okay, now, 3.5 is or is not in the chart. Is 3.5 in the chart? No, it's not. But notice if it were, it would fall somewhere between 3 and 3.6. It would fall somewhere in here. So in this case, it makes sense to use the two values on either side of where 3.5 would live. So we'll use that, 16 and 38.2. 16 minus 38.2. All over the change in the corresponding x values, which is 3.6 minus 3. Now I'm going to stop right there. I'm not going to simplify. So what's important again is to, three things really, right? Show a difference quotient. If you prefer to put s of 3.6 minus s of 3 over 3.6 minus 3, that earns credit for the difference quotient. And then you can do all mental math after that. But it's easier if it's from a chart to just show the difference quotient with numbers, which is a numeric answer, which you could stop on a free response, putting units, of course, if there were any. And then the other important thing is don't get confused and just do 3 minus 3.6 all over 38.2 minus 16, right? Because what's wrong with that? Right. You're doing the change in x over the change in y instead of the change in y over the change in x. Now, if you flip those, it would be okay, but that's what I told you I'd prefer you didn't do. I'd still prefer if you did final minus initial over minus initial. But as long as they correspond in the quotient, it's going to give you the same answer, right? But when you do final minus initial, you're reinforcing the displacement aspect of it. Okay, Al Roker White House, too, apparently, is a popular. All right, part E, party. From the information given, is it possible to determine the time and the position of the bug when it's farthest away from the origin? Hawaii or Hawaii not? Is it possible to determine the time and the position when it's the farthest away from the origin? Well, let's see. Assuming that it's, again, moving on a vertical line instead of a horizontal, the origin would be kind of, whatever the line is, it would be the benchmark point of reference, which we're going to call 0. Is it possible then to determine when it's farthest away from 0? Well, when it starts, it's 40 units away. And, oh, look, there it's 48 units away in the positive direction. And it never actually ends up on the other side, right, of 0. So, or at least it looks like that from the data. Is it okay then to say that at t equals 2 seconds, the particle is farthest away from the origin at 48.2? Why or why not? Why not? You're right. The answer is no. Absolutely, yeah. It could have gone between 2 and 2.7. It could have gone up to 49, or 490, or 4,900, right? And that would be the farthest away. Or hey, it could have gone from 2 to 2.7. It could have gone down to negative 1 million, and then darted back up to 45, right? We don't know. Oh, because the word estimate is there, then we can just say, yeah, this is just an estimate over an interval. Yeah, it's not necessarily accurate. Yeah, exactly. How good are these numbers? You got me. But they are the best estimate that we can provide given the data. And that's the whole thing about the data. Okay, we are limited by the data that we're given, and all we can do is predict from data. If we wanted to know more of the story of the bug, we could have been there and collected our own data points, right? We're at the mercy of the data. So, no, since we only have data points at, what do you want to say? At a discrete number of points or at finite values, semicolon, we don't know any information. This could be in lieu of, we don't know any information about the bug's position. On or at any other point, right? At any point not given. Something like that. Something that basically says, no, we only have these data points. We know that the bug was doing something in between those data points, and what it was doing, it's anybody's guess, okay? Kind of like some of Trump's ideas when he gets to the White House. It's anybody's guess. We don't know. He just gives us finite little data points that are... But they're going to be the best. They're going to be the best, right. They're all going to be in superlative. All right, we are done with particle motion number 1. Of course, course, then we just have to practice. And what's the third one? Practice. Yeah. So the worksheet will be due tomorrow for 2.5. Tomorrow being Friday, that's kind of a good time for our particle motion quiz as well. So be ready for a quiz. All right, any questions on 2.5? Fun.